plan for today is to go over the Immerman-Szelepcsenyi theorem, a celebrated theorem that proves that NL is equal to co-NL. Quite a surprise that complementation of non-deterministic space classes actually doesn't change the class. And in general, one can prove that for any function, any Sn that's omega log n, non-deterministic space of Sn is the same as co-non-deterministic space of Sn, and that's by a padding argument. So I'm going to walk through the argument that I had in the previous lecture, where I was sort of building the basics of the argument, and I'll walk through that again, take any questions on that, and then I'll just sort of give you the full proof. Okay, so what we know is that the language path is NL complete. And therefore, path complement is co-NL complete. And this was actually an exercise, this was a question in one of your homeworks, and the same argument works over here. So path complement is co-NL complete. Remember, it doesn't matter whether it's co-NL complete or co-NL complete, right? So let's say it's co-NL complete, which means that any language in co-NL can be reduced and sort of with a log space reduction to the complement of path. So if we can show that path complement is in NL, then we'll actually prove that NL is equal to co-NL. I left that as an exercise. So if we prove that path complement is in NL, then NL is equal to co-NL. So what is path complement? It's the language GST, where G is a directed graph, and S and T are not connected, that there is no path from S to T. Okay, that's the language. So now you can forget about everything else. Say, okay, so I have this language which is G is directed and there is no path from S to T. Now the fact that path is in NL is kind of obvious. So when in path, then there is a path from S to T. The non-determinism is simply the path. And we can also think of non-determinism in terms of a read once certificate, as we discussed. So the read once certificate would just be the path. So think of a certificate that you can read only once, and at every step you basically look at the next vertex on the path and you follow it down and get to the end. Okay? But how can non-determinism prove that there is no path? And this seems almost like it's impossible, because non-determinism is all about saying that if there exists a non-deterministic path, then you accept the language. How can non-determinism prove that there is no path? And we sort of dealt with this when we were talking about SAT and tautology. And we said, in some sense, tautology is different from SAT. It's co-NP versus NP. And at that point, you might have thought, it just doesn't seem possible that NP could be equal to co-NP. Because how can you use non-determinism to argue that all assignments are going to be true? But remarkably, for path, you can prove that NL is equal to co-NL. So now, in some sense, this, it throws a spanner into the way you think. Like your intuition now is almost for me, my intuition is now shaken. Like if non-determinism can actually prove that there is no path, then maybe it can also prove that there is no satisfying assignment. Of course, we don't think that is the case, but just throwing that out there. Okay. Let us now go to the proof that path complement is in NL. So we are going to think in terms of read once polynomial sized certificates, and that is sort of the right way to think about it. A non-deterministic log space machine is just it's too complicated. So we're going to think in terms of polynomial sized read once certificates. And if you may have observed that in a lot of the proofs involving space complexity, you always sort of parameterize by some kind of distance, like just as we did in Savage's theorem, that and even in QBF, you look at this configuration graph and you say, okay, you want to have a path from S to T, and then you try to find a vertex in the middle, and then you look at the log of the length and things like that. So the length of the path seems to be useful. So let me define this language path complement I, which is just saying that path I is the language where S and T have distance at most I. So path I complement is that there is no path from S to T of length less than or equal to I. Alternately, let distance dst be the shortest path distance from S to T in the graph. Path I complement, and we'll say the distance is infinite if there is no path. Right? The distance is infinite if there is no path. Path I complement is GST such that the distance between S and T is strictly greater than I. That's what path I is. Now the convenience of path I with respect to the original path problem is path n-1 complement is just path complement, which means that if the shortest path distance is more than n-1, then it's infinite. Right? Because if this is just, it's a directed graph, right? So if there exists a path between two vertices, then there exists a path of length at most n-1. Because if the path cycles itself, you can just remove the cycle. Right? A shortest path distance on an unweighted graph is at most n-1. So what we are going to do is we're going to construct read-once certificates for path I complement. From those, we're going to construct read-once certificates for path I plus 1 complement, and we'll sort of inductively build this. Instead of showing you directly the proof by induction, I want to walk through it slowly by looking at path 0, path 1, path 2 complements. This technique is called iterative counting, and you'll see why it's called iterative counting shortly. We'll think of G being an adjacency matrix. Okay. So what is path 0 complement? Path 0 complement means it's GST such that the distance between S and T is more than 0. If the distance is more than 0, it just means that there are different vertices. So path 0 complement is the language of GST where S is not equal to T. This is clearly in log space, right? Because the sizes of S and T are log n bits, so the log space machine can just read those and compare them one by one. Let's look at what path 1 complement is. Path 1 complement is GST, where now S is not equal to T and ST is not an edge. Because if ST is an edge, then the distance would be 1. And so this is something that would not be in the language. We're looking at the complement. The shortest path distance here has to be strictly greater than 1. And this language is also in L. Why is it in log space? Because you can always compare S and T in log space, and then the log space machine just has to go and do one lookup in the input. So think of it as what the log space machine is doing is it does lookups in the adjacency matrix, and it goes and looks up that one position and says, oh, there's no edge over there, or there is an edge over there. Things get interesting when we look at path 2 complement. This is the language of pairs of vertices, so GST, where the shortest path distance from S to T is strictly greater than 2. Is strictly greater than 2. Now what does that mean? It means that if you look at the out neighborhood of S and the in neighborhood of T, these neighborhoods excuse me, are disjoint, because if they intersected, you would have a path of length 2. So this is path 2 complement. We are now going to show a read-once certificate for path 2 complement. So what does it mean to have distance more than 2? The distance is 2 if and only if for all vertices in the out neighborhood of S, V comma T is not an edge. This condition, V comma T being not an edge, can be checked in log space. So this is good. So we're saying that this is like a for all condition where the predicate can be checked in log space. So let's give a first attempt at a read once certificate. Note that the certificate can only be read once. Let's say the certificate is actually the out neighborhood of S. So the certificate is just going to be V1, V2 up to Vk, which are the out neighborhood. Let's construct the verifier. The first thing that the verifier does just is check that ST is not an edge and S and T are distinct. Like this it can do. Then what it does is it says for all vertices in V1 to Vk, check if SV is in E, meaning that check if V is actually a neighbor of S. And if it isn't, reject, because that means a certificate is incorrect. That means that the certificate is incorrect. So first make sure that the certificate is correct. This is checking the correctness of the certificate. Step B then says, okay, I know that V is an out neighbor of S. So V is an out neighbor of S. Then one has to check if the edge VT exists. If VT exists, then you reject because you found a path of length 2. So you know that this is not in the language. And you apply, the verifier applies this for all the vertices in the neighborhood. Now the problem is this certificate is defective because maybe there is some neighbor V prime of S that is not listed in the certificate. How does the verifier know that the certificate contains all the out neighbors? It can check that each of these vertices, V1 to Vk, are individually out neighbors. But maybe there is some other vertex that is not an out neighbor. Now you could say maybe the verifier could loop over all vertices. But if it loops over all vertices, so the problem is it cannot go back and check if they're in the certificate. Right? It cannot go back and check whether it's in the certificate. Now you can actually see that, potentially you could try to sort of get a log space machine to do this, like loop over all the vertices. Right? It's going to loop over all the neighbors, but it cannot go back and check if it's in the certificate. So we'll actually see that, how this is going to work. So what the certificate is going to do is actually contain the out neighborhood size. And then it has the out neighborhood in increasing order. This is to prevent repeats. Now the verifier has to be able to check if the certificate is accurate, so that it's not fooled by the certificate. So it can store dv plus from the certificate. And you'll see that this is somewhat redundant. The verifier could have actually computed dv plus. But the reason I'm saying this is to show you an inductive substructure. So it could compute dv plus. It can compute the out degree, right? It can just look at the graph and go and look up the entire adjacency matrix row, and it can compute. And it can check, does it match? Yes, it does check. Then it goes ahead and takes care of it. If not, it rejects. And then what it does is for every vertex v1 to vk in order, it goes ahead and checks. It checks, it basically applies the check before, right? It goes and checks, is this a neighbor and whether it's connected to T. And then finally it checks whether the number of vertices over here that it's seen is actually equal to the out degree. And if not, it rejects. So you cannot fool the verifier. It has to get a certificate that is correct. Okay, so this is the extent to where we got. Are there any questions at this point? Any questions about this construction? It's clear?
Certificate is trying to show all possible ways that you can try to find a path, and then the machine verifies that none of these actually work.
Exactly. And the machine is also convincing itself that this exhausts all possibilities.
Yeah. All right.
Okay. So I'm going to now introduce some definitions here, some sets. So I will refer to the set BI, which is the distance I ball from S. This is simply all vertices V, such that the distance of S to V is at most I. Right? And so B0 is just S, B1 is the out neighborhood of S, so on and so forth. What I am now going to show you, and this is the iterative counting part, is that given the certificate that we have before, so from what we have before, there is a read once certificate of length O of n log n, right? It's basically because there are at most n vertices here, and the length of each vertex is log n bits. So the certificate length is n log n bits. There is a read once certificate of length O of n log n, right? There is a read once certificate of length O of n log n for V such that dsV is strictly greater than 2. Note that there is a read once certificate of length O of n log n for V such that dsV is at most 2, and this is just the path. Just the path of length at most 2. It's even better. It's not even n log n, it's just O of log n. Right? It's even better. It's just O of log n. So there is a read once certificate for a vertex of length greater than or equal to 2, and a read once certificate of length less than or equal to 2. Now using this, we can construct a read once certificate for the size B2. So the size, so we're saying what we're going to do is you can think of a vertex S, and here are all the things at distance. This is like B1, and then this is B2. So this is saying that there is a certificate of a vertex lying in B2 and a vertex not lying in B2. So this is V is not in B2, and this is V is in B2. So there is a certificate for any vertex. We can give a certificate that says this vertex is in B2 or not in B2. Using that, you can imagine we can construct a read once certificate for the size. How are we going to do that? So let me sort of draw out the certificate. So the certificate is first going to contain the size of B2. This is like, I'm going to give a read once certificate that is going to convince a log space machine of the size of B2. Then it's going to number the vertices, all the vertices in order. So it's going to say, let's start with vertex 1. And then it's going to have a certificate that maybe it says 1 is not in B2. Then it just says 2. And maybe the vertex 2 is in B2. So these are the certificates for these. These are the read once. Certificates. And then for 3, it has some certificate. Maybe 3 is also not in B2. so on and so forth, goes all the way up to n. I would say n maybe is in B2. So it can read this entire thing once and just check if the number of things that are in B2 is exactly what it was given. Right? So the verifier stores the certificates claimed B2. So it's sort of like, think of it as the verifier is this small machine, it's log space. And it's trying to be convinced that there is a particular size. So the verifier needs to be convinced. So the verifier says, okay, is 1 in B2 or not? And the certificate says 1 is not in B2. Here's the certificate. So it can go and check the certificate based on what we did so far. Then it says, okay, tell me, is 2 in B2 or not? And it says, yes, it's in B2. Show me the certificate. So as it goes through this, the verifier can just count how many times it's seen a vertex in B2. Right? And for each vertex in order, so it can, because it can store, right? It can say, okay, it's almost like an index. It's storing, now I'm looking at index I, vertex I. And the certificate is going to tell me, is I in B2 or not? So for every vertex in order, right? For every vertex in order, it gets this certificate of whether things are in B2 or not. Every vertex in order, the verifier gets a certificate for V in B2 or V not in B2, and verifier keeps track of the number of vertices in B2 and verifies and checks this is the same as what was claimed. Right, so the certificate claims some value. It goes over all the vertices. Then it gets a certificate, yes or no, yes, no, whatever, and it counts how many yeses were there, and it says, okay, now it's sure. So what is important is that because it has certificates for not being in B2, it can actually keep track of which vertices are not keep track of which. So it can keep track of the number of vertices that are not in B2, and it's not going to get fooled. If this certificate did not exist, these are easy. Being in B2 is easy. But how does it know that some vertex is not being missed? So it needs to get certificates for all the vertices of not being in B2. Does this make sense?
I would imagine that one way you can have this certificate would be to have essentially the certificate would be a bit vector, or a bit vector, which would say like 1 if the corresponding vertex is in B2 and 0 otherwise. Like you said,
right, but I mean it can get that, but then for each bit of the bit vector, it needs a certificate that that bit is correct. Does that make sense? I mean, let's say that, so this log space machine basically gets a certificate saying these are the vertices in B2. So it can go through that bit by bit. But how does it know that it's not being fooled?
Well, I'm saying if it's a bit vector, then it's going to say it for all of them anyways, and they're going to be in order.
Sorry, maybe I'm misinterpreting what you're saying.
So what I'm suggesting is that one possible certificate would be to have if there are n vertices in the graph, then you have n bits in the certificate, where 0 indicates that it's not in B2, and 1 indicates that it is in B2. And every single vertex will be accounted for because it's going to be in order.
Right, but it also needs to certify those bits. So what you're saying is, okay, so let's just say that V, let's say the certificate. The point about the certificate is not that, if it's correct, it's fine, but what if it's wrong? It should not be fooled by an incorrect certificate. So if it got this bit vector from 1 to n of like zeros and ones, how does it know that the certificate is not lying?
I can check.
Is this true? But how could it?
Isn't that the point of listing the size of B2 at the beginning?
So the size of B2 is actually not that important. I'm just sort of saying that could be part of the certificate. The point is it can count how many things are in B2.
Right.
But I want to sort of emphasize this. How does it check that something is not in B2? Or how does it check that something is in B2?
I don't think we haven't established that yet.
No, that is what we have done so far. So maybe that is, let me go back to what I said earlier, that there is a read once certificate of length n log n for the distance being greater than 2. There is a read once certificate, and that read once certificate is the out neighborhood with the degree.
But doesn't the bit vector imply the out neighborhood? Or
so the thing about the bit vector is that it needs to know that the bits are not incorrect.
Oh, I think so. Are you saying that every certificate on the other page, every certificate, that says, that says whether something is in B2 or not, that is the certificate from before?
Exactly.
Talked about. I see.
So that is this thing that I've said here. These certificates which we described, that certificate is in here. So it's not just a bit. It's actually this entire long-winded thing. So when it's not in B2, it has the entire out neighborhood. The out neighborhood is given over and over again.
I see.
This is the read once certificate of this fact.
Oh, okay. I see.
Right?
I interpret it as just being a 1 or 0 sort of thing, but okay. That is a certificate itself.
That is a certificate itself. So this entire long thing which is n squared log n bits certifies the size. Excuse me. That certifies the size.
Okay, I follow.
Right? And the important point is that the running time of the verifier here, the verifier is just going to be like, something that runs in it's just log n space, right? It doesn't need to remember anything. Like it has absolutely, it just remembers, all it does is it remembers the size of B2, and then it has some auxiliary space to check the certificate, but then it can just reuse that space. Does this make sense? That we can actually construct a read once certificate for the size B2?
Right. And because the other certificates were all read once, then everything works out.
Yeah,
right?
The whole thing is read once.
Right.
Okay, and now I'm imagining that if we are trying to do it for the next level, for B3,
exactly,
that we can use these certificates, or for example, we could use we could try all of the possible like things that are one step away, or that may be one step away, like
that are 2 steps away. So good. So what we're now going to do is so let me start writing, and then you can guess what I'm trying to do. So hopefully this makes sense. So there is a read one certificate for B2. What this means is you have a log space machine that can be convinced of the value of B2. I want to draw another picture, and I think this picture is very important to understand what's going on here. And think of it as there's a huge graph here, massive graph, and there's this little log space verifier. V has very little storage. It can basically store like a constant number of vertices. That's it. V can only store O of 1 vertices or numbers, because each of these is like O of log n bits. That's pretty much all it can store. V can look up the graph. Now V, you can think of, is trying to learn something about the graph. And I want to give this image of, you're trying to learn something about the internet graph, which is this massive graph, whereas your computer has limited storage. And you're trying to learn something about the graph. So you or the verifier is trying to learn something about the graph. And so the verifier is asking, is D of SV, so there's S and here's V. Is D of SV greater than 2? And let's say it's talking usually what's called a prover, who's sort of like an adversary. And so the prover says yes. So the verifier is going to say, prove it to me. Prove it using a read once certificate. And so now what the adversary has to do is to come up with this read once certificate, which is of poly n size, so that the verifier can make one pass over the certificate and then say, okay, I'm convinced that it is not. Remember, if it was the opposite, if the prover wanted to prove no, that's easy. To prove no, it can just say, here's the path, which would just be of log n size. But to prove that it is actually not of length 2, a distance is more than distance 2, it has to give this one certificate, and that certificate is going to be this fairly long and complex certificate. But once it goes through that entire certificate, by the time it finishes, the verifier is convinced that the distance is at least 2. This is sort of the mental picture that I want you to have. Is this clear? What is, again, I want to emphasize, what's interesting is that B2 may have huge size. Don't think of the vertex degrees as constant. The vertex degrees might be n. It might be huge. There is no way that the verifier can even store the neighborhood. But yet it can be convinced of this fact.
Can I throw out what I'm thinking?
Sure. Yes. This is a good time to throw out your idea. Yes.
Could you actually go back to the previous
I will go
page?
back to the previous picture. Sure.
It actually is a little more convenient for...
Yes. So here's the picture.
I'm thinking that if we want the certificate to prove that a vertex is in B3, then there must exist some vertex that is within B2 of the original source, and there has to be an edge between that destination and the intermediary thing.
So sorry,
And
just to interject, proving that a vertex is in B3 is easy because it's just a path of length 3.
but I'm trying to suggest it in a way that you can do it inductively.
But I'm saying that showing that a vertex is in BI is easy because it's just a path of length I. The
I'm
challenge,
about to also say how to prove that it's not.
that is the hard part, exactly.
Yeah. As for showing how it's not,
Yes.
I'm thinking that you have to.
Exactly. How does it show that a vertex is not in B? Sorry, yes. How is it not in B3?
I think you would have to show that there is no vertex where it is both in B2 and has an edge with your
Exactly.
destination.
Exactly.
Yeah.
Now
So
note that
you-
the verifier can look up single edges.
Yeah. So the certificate would be to show that for each of these individual vertices, it fails that condition that, first of all, that intermediary has to be in B2 and also there has to be an edge.
Mm-hmm.
But I am thinking that for this, it would kind of be like a times n sort of thing, or like it would be one polynomial degree larger. So I'm not sure if it will work out exactly. I think maybe we need to, or I'm guessing kind of maybe we need to employ the midpoint, so the midpoint sort of thing that we had for like proving p spaces and np spaces.
No, we can, but if we're careful, it's not going to blow up as much. So let's see if we can do this. So B2, it has this certificate of length n log n square log n. So let's just say that now let's just try to get a certificate for B3. So how do we get a certificate that V is not in B3? A certificate. So what it needs is all vertices in B2. So I'm just describing the certificate in increasing order for each vertex in B2, certificate that V is in B2. And then the size of B2. So I'll draw it out here. So it has, what it gets is, it gets B2. It gets a certificate for B2. And then it gets V1. The V1 is in B2 certificate. V2. V2 is in B2 certificate. V3. V3 is in B3 certificate, so on and so forth. Now note that this certificate doesn't have to be, this portion doesn't have to be repeated n times. So we'll just say this certificate appears, okay, so sorry, ignore what I'm going to say. Sorry, ignore that. Let's go back to this. V is in B3. V is not in B3. This is the certificate. So how does the verifier work? The verifier first verifies that the size of B2 is correct. Then for each V in V1 to whatever, let's just say it's Vk, for each V in V1 to Vk, check that, I'll say each Vi in B2 is a correct certificate, and then check that Vi, sorry, let me, instead of T, let me just call this T, so just to give it a different vertex. Just check that VIT is not an edge. And this gives a verification. This gives a verification of V of T not being, so if you have a vertex T, then it is not in B3, that is a certificate. So first a certificate for the size, then this. Does this make sense?
So certificate for the size of B2, is that just verifying that you have all of the vertices?
Exactly, yes.
Anyhow?
Yes, so this is, and then finally check that K is equal to the size of B2, just to make sure that you've seen all the vertices.
Gotcha.
So this is sort of common for any T. The same for any T. Indeed, even this is the same for any vertex T. Now, it's just the same thing. If you think about it, the certificate has nothing to do with T. It just has this. Now, what is this? This is just a series of paths. So is this clear? So now let's get a certificate for B3. Because now if we can get the size of B3, then we can do it for B4, and so on and so forth. And you'll see that the increase is not going to be multiplicative, but it's going to be additive, the length of the certificate. So to certify B3, first you get the size of B3, okay, so whatever the size is. Then you get the size of B2, the certificate for the size of B2. Okay, so this is giving B2. And then there was this portion here, which I'm just going to put over there, n times. So this certificate is simply the list of all vertices in B2 with the size, with the certificate for each. So it's just saying that once you know what the size of B2 is, the verifier can just check whether all of those are in B2, and this is used to check if 1 is in B3. This is used to check if 2 is in B3, so on and so forth. So on and so forth. If you think about it, this is just a list of n paths. This is a list of n paths, right? Because each of these certificates, this is just a path, right? This was just a path. So it's at most, I mean, we're saying it's of length 2, but it's just at most of length n, regardless of what size I'm looking at. So it's just at most n paths of length n. So this is, each of these is n paths of length n. So that's basically O of n square log n bits. And of course, the total length over here is just O of n cube log n bits. And at the end of this, so once the verifier reads all of this, the verifier is convinced of the size of B3. Right, at this point, the verifier is convinced of the size of B3. Once the verifier is convinced of the size of B3, it can then be convinced of the size of B4. And finally, once it's convinced of the size of Bn minus 1, then it can just go ahead and check for all the vertices. Okay, but maybe I'll get to that. So is this clear? And this is to answer the question why things are not blowing up exponentially. At any stage, the verifier is going to get n paths of length n repeated n times. From there, it then is convinced of the next size. And then it gets n more paths of length n repeated n times, and then it's convinced of the next size. By the next size, I mean B2 to B3 to B4, so on and so forth.
So each step in the process is at most n squared log n, and there are at most n such steps, so it becomes n cubed log n.
So I guess technically it's n cubed log n for going from bi to bi plus 1, and then that is repeated n times. So it's n to the 4th log n, because this entire thing has to be repeated n times. Right, because this only gets you from B2 to B3.
Okay, I follow.
I have a question.
Yes, go ahead.
Wait, so why do we have to repeat this n times or for t in B3? Like, why can't we just check them all at the same time, right?
Well, you see, the thing is, to check t, you have to loop over all the vertices.
Right.
But then to check the next vertex, you have to loop over them again. It's a read once certificate, right? So think of it as the verifier has so little memory that it cannot afford to check all the vertices together.
Oh. I was gonna say, is it not possible just to have all the list of all the vertices, and then for each of these, for each of these cells, just check if if there is a edge between V1 and T. But I suppose is the memory a constraint then?
Right. So the verifier is log space. So think about the verifier can store like a constant number of vertices in memory.
Right.
So the verifier cannot store a list.
Okay. Oh, sure. Okay.
So it cannot store like the list of it cannot even it can loop over all vertices, but then it can't do like an all for all check. What you're saying is like, here's all the vertices. It's got all the vertices. Every time it sees V1, just check with all the vertices that it's got.
Yeah.
Let me see. So wait.
On this note, I will also remark that probably the most compact way to represent a set of vertices would be to use a bit vector, because then they'll take at most as many bits as there are vertices. But if we got an adjacency matrix as our input, then the number of vertices would be about square root of n. So it's
think of n as the number of vertices. It's more convenient, right? N is the number of vertices. So okay, let me try to actually answer that question. So this previous question would say that okay, so now that you have V1, the machine could loop over all vertices and figure out which of those are in B3. That's what you said, right?
Right, exactly.
But then it goes to V2. It cannot remember which of the vertices it ruled out. Does that make sense? So here's your verifier, right? Your verifier is looking at this. It's sort of walking through this. So after looking at V1, so let's just say here's your graph and here's V1, and there are a bunch of things that V1 is connected to, and so the verifier can loop over and figure out how many. Then it goes to V2. But then V2 may also be connected to the same vertex, and it shouldn't be considering that vertex again, because it's already said this is not in B2, but it cannot remember all of that.
Wait, but I mean, would that only be a time, an inefficiency in the amount of time?
No, and it's space. Like the verifier cannot store which vertices are in B2.
Right.
It can store a count, but then it would be overcounting because there are some vertices that may be connected to many vertices in B2. Like let's say this vertex is connected to 3 things in B2. This is sort of bad. Let's say all of this is in B2. Right, this is B2. And there's one vertex that only has one connection, but there's some vertices here that have many connections. Okay, the arrows are drawn badly, but it's okay. So sorry, this picture is bad. Let me try to draw it elsewhere. This it's good. Like this takes some time to understand like what's going on over here.
Yeah.
So here's your certificate. What you're saying is, why isn't the certificate just appear once? Or maybe I'm not here, but rather here you're saying, why does it appear n times?
Yeah, exactly.
Okay. So what I'm saying is, with the certificate, you can check if 1 is in B3.
Right.
Let's say you wanted to check if 1 is in B3 and 2 is in B3 and 3 is in B3. All 3 of them. You're saying you could check all of them simultaneously.
Right.
But how many such things can you check simultaneously? Only a constant.
Oh, I think I see what you're saying. It's because you can't just store which ones you found out. Right?
Exactly.
Right. Okay. I see.
So the verifier can't. So think of it as the verifier basically, in some sense, has no memory. Maybe the best way to think of the verifier can store like 3 counts. That's it.
Right. There's no way it can't. It's not allowed to store because to keep track of everything at each block, it would have to store like basically something for every single vertex. And
Exactly.
It can't do that.
It cannot store a bitmap
I see.
because that would be n bits, and it only has log n space. It's remarkable that you could do anything. The verifier can only store a number. That's it.
Yeah, it's a bit subtle, but it makes sense.
Yeah, it is subtle, right? You have to think about it carefully, right? I mean, so
Yeah.
think of it as like you're trying to determine like whether, I don't know, in the internet graph, whether you can get from one page on Wikipedia by clicks to, some other website. And you don't have enough memory to even store what vertices can be visited by like a crawl or anything. All you can store is like one link, one website. That's it. Or maybe a constant number of URLs. And you want a certificate that's going to convince you that there's no way of getting somewhere. So the only thing that sort of convinces you is the count. What this method does is iterative counting. It tells you that if the adversary convinces you what the size of BI is, it can convince you about the size of BI plus 1 even though you have limited memory.
I see.
So there was some question regarding bitmaps. I just want to clarify that. Like, do you see, a bitmap is too large. Maybe what you're saying is you can save on the size of the certificate?
Maybe he stepped away for a second, but I think he was suggesting that you could store like all of the nodes, all the vertices as like instead of just like as an adjacency matrix as some kind of bitmap. But obviously that would still be O of n size, so that would still not work.
Yeah, the verifier cannot afford to store any of it.
Yeah.
And so, like, once we have this, let me just write this one more time so that we kind of understand. So think of it as the verifier is going through this process. At this point in the process, the verifier is convinced of B3. The verifier has the value of B3 and knows it's correct. Once it has the value of B3, then what it can get is a certificate, which is each VI in B3 with a certificate that VI is in B3. And this is easy because this is just a path. So what it gets is V1, and let me just write this as a path. So it says it gets a path, a certificate that VI is in B3. So it's a path from S to VI of length 3. I'm going to write this. This means path of length 3 from S to VI. Right? So this is going to give it a path of length 3 to V1. Then it sees V2, and then the path of length 3 to V2, so on and so forth. So once it has this entire certificate, this certificate is enough to determine if T is in B4. The length of the certificate, the length is O of n squared log n because it's just n paths of length at most n. This certificate convinces the vertex whether T is in B4 or not. T is not, either this or not. And so now we have a certificate for a vertex being in B4 or not B4, so you get all those certificates. And once all those certificates are given, then it can convince itself of the size of B4, from which it then goes to the size of B5, so on and so forth. Is this starting to make sense? And again, go and look. Aurora Barak has a fairly condensed, but sort of accurate description. Of course, accurate, but it's somewhat a condensed picture of this. It's useful to draw this picture to really see what's going on, see the cleverness. And so it's amazing that you can actually give certificates for something not being in the set, use that to count the size of the set, and that's why it's called iterative counting. By just counting the size of these balls, these iterated neighborhoods, you can determine things are not in the neighborhood. And so I'll write the whole inductive picture, and I'll just say that if a log space machine can be convinced of BI, then given all vertices of BI in order with a certificate of V being in BI, the machine can be convinced that a vertex T is in BI or not. So T is not in BI because that's the hard one, or not. Because once it gets all the vertices of this in order, it can just go and check if any of them is a neighbor or not. And this is important because to check that it has all the vertices, it needs to know BI. To ensure it has seen all vertices in BI, it needs the size BI. By it, I mean the machine. And because of that, it needs the size of BI. Then by going over all vertices and seeing all of BI n times, it can count BI plus 1. So eventually, it can count B of n minus 1, which is equal to the number of reachable vertices. So once it knows the number of reachable vertices, then it can get a certificate. This gives a certificate that T is not in Bn minus 1, meaning GST is not in path. And that completes the argument. So obviously I didn't write everything down in gory detail because at some point the details can distract one from the main idea. So I want you to see the main idea. And I think the main idea is sort of encapsulated in this picture here. And one can even sort of ignore this part and just say that once you get a certificate for B2, Then you get all the list of vertices in B2. You know that you're seeing all the vertices. The log space verifier knows it's seeing all the vertices. It gets a certificate for every vertex on the path. It uses it to check, is vertex 1 in B3? Is vertex 2 in B3? So on and so forth. Then it can count how many vertices are in B3, and then goes through this process yet again to count the vertices in B4, so on and so forth. The certificate size is basically O of n to the 4 log n, because this entire process, or this entire certificate is, or this, this is sort of repeated n times, or for every length, the certificate will change, but then this whole sort of paradigm is repeated n times. So you get n to the 4 log n. And that is the total size of the certificate. Any questions about that? Any questions? Please stop and ask me if there's any doubt.
So what's the total runtime of the? Or well, I guess what's the total size? Would it be n to the I log n?
No. The important thing is it doesn't depend on I. It's just n to the 4th log n for any I. It's technically like n cubed times I log n.
N cubed times I. Oh. Okay.
But I is just n, right? So it's n to the 4th log n.
Okay.
This is essential that it's not n to the power I, but rather n times I.
I see.
This is essential, because if it was more, then you're right. Then it would be an exponential size. It has to be a polynomial size certificate.
Right.
Just think of it as all it's seeing is a collection of paths. Like the certificate just consists of lots of paths between vertices. It's seeing those paths over and over again, or sometimes. Like it's got a bunch of paths of length 1, then a bunch of paths of length 2, then a bunch of paths of length 3, so on and so forth. Each path has length at most n. And the total number of times it sees anything is really n cubed. So there will be n to the 4th log n is the size of the certificate.
But on the next level, doesn't it that have to repeat n times again, like going from from B3 to B4, and then from B4 to B5? That's another n times it has to repeat, right? So you're doing that I times.
No, right? So what's important is this entire picture is not going to repeat n times. No. So this convinces it of B3.
Right.
Once it knows what B3 is, it just has to see something like this once to be convinced of B4. Because this itself has n things in it. So think of it, this thing is just repeated n times. Let me draw this out again. So let's say that think of it sort of maybe more as a process, right? So at this point the verifier is convinced of B3. Let's see, what is it going to take for the verifier to be convinced of B4? What does it need? Well, what it needs to see is all the vertices of B3 in order, with a path for each of those vertices convincing that it's in B3.
Right.
This is n paths. At most n paths of length n. This is enough to convince it whether a single vertex is in B4 or not.
So each one of those, it doesn't have to display the entire certificate that a vertex is in B3 for each of those cells.
It sees this certificate. But
right.
But having a distance of 3 doesn't need all of this complicated stuff. Having a distance of 3 is just a path. So it just sees the path, which is really just going to be at most of length n. In this case, at most of length 3.
Okay.
It's just seeing. So think of it as once it knows what the size of B3 is, it can store B3. It doesn't have to be convinced of the size of B3 over and over again. Maybe this is what I should have said. Once it has B3, it can just store the count B3. It doesn't need to see this certificate again and again to be convinced of B3 over and over again, because B3 can be stored. And once it gets B4, it can forget about B3.
So first it figures out what's in B3, and then it just stores that. And then later on, when it goes to B4, it doesn't have to repeat any of that. It can just say, oh, well, I know if this is in B3, then just use that.
So once it knows the size of B4, it doesn't know anything else. All it knows is the size of B4. That's it. It doesn't remember which vertices were in B3 or B4. Let me draw this again. I think this is a point of confusion. Okay. So let's say at some point, Verifier knows BI. Right? We're saying at some stage, inductively, it knows what BI is. Now what does it need? So let me draw out exactly what it has. So I'll say a basic block. So let me call it a block. A block, a certificate block, has each vertex in BI followed by a path from S to V of length I. This is what a certificate block is.
Okay.
Now what is the size? Size of a certificate block is O of n squared log n. And because the verifier knows BI, it knows that this certificate actually has all the vertices in BI. Because this part can be checked easily.
Okay. I see. So the paths are easy to verify, obviously, and then we just have to make sure that we have all the paths.
Exactly.
Which is again verifiable.
Because it knows BI. Because it knows BI.
Right. Because it knows BI, and then we just have to go through that other process that we mentioned before, just checking to see if there's a edge between T and all the VIs, right?
Right, between VI, exactly, VI and any T, right? So we have to just do this process.
Okay.
Let me write this down again over here. So this is what a certificate block is. So hopefully you know what a certificate block is. So I'll call this the certificate block. Okay? Now, given a vertex T and one read once certificate block, verifier can determine if T is not in BI plus 1 or T is in BI plus 1. It can determine exactly because it can verify the read once certificate block. It can check that this block is correct. And if the block is correct, then it can determine is it in BI plus 1 or not. Right?
Right.
So that means that with n read once certificate blocks, verifier can count the number of vertices in BI plus 1. Because for each block, it just goes ahead and checks vertex 1, vertex 2, so on and so forth. So it can basically loop and it can count. It needs n blocks.
So I guess what I assumed before was that I saw all those blocks for B2 and B3, and I guess what I thought before was that we were sort of stacking all those blocks on top of each other, and they're nested. But
No.
really, it's not that.
No, it's not.
Really, it's just that we have B2 to convince ourselves that that something is not in B2, and then once and then we can go into B3, but B3 doesn't contain B3 necessarily. It's really just that we have a path from a path of length 2, and then which is easy to verify, and then we just check for each of those. That's one block, and we just check for each of those, each key, and that will tell us if it's in B2.
Exactly.
B3
The point
or not.
is, once you get the size of BI, the subsequent certificates in this block have nothing to do with how we convinced ourselves of BI. So the verifier convinced itself of BI through some complex process. But this certificate block, in some sense, doesn't care about that. It says, okay, you know what BI is? Now let me convince you that I'm showing you all the vertices in BI.
So, was the purpose of going through, like, we showed B2 to B3, right? And obviously we showed B1 to B2. Was that just like as part of a proof, or is that something that the verifier actually has to do?
It has to do that because it has to go from BI to BI plus 1. I mean, I demonstrated B1 to B2 and B2 to B3 just to sort of give you intuition.
Okay.
But of course, but think of it this way, right? It has to go from BI to BI plus 1, and all of this has to be repeated n times, but it's not nested.
Okay.
It's not a recursion. It's just a loop. It's important if you read this description, there is no recursive reference for a read one certificate of BI.
Right.
The certificate block is just a collection of paths. And what we need is to see the certificate block n times.
Okay.
The certificate block size, this n squared log n, is independent of I. It doesn't depend on I. It's just n squared log n regardless of which I, because it's a collection of paths.
I see. So really, we just have a collection of paths, and then for each of those paths, we just have to check if there's an edge at the end of that path to whatever the destination edge we have.
Exactly.
I see. Thank you.
So then the verifier can count the number of vertices in BI plus 1. So now the size is O of n cubed log n. The total certificate size. The total for this part, certificate size to go from the size of BI to the size of BI plus 1. And so overall, it's going to be n times this, which is O of n to the 4th log n, to go from B0, which was just 1, to how many vertices are connected in the graph. How many vertices S is connected to in the graph, to that.
At the beginning, you said that trying to prove this thing using a non-deterministic machine rather than using certificates would make you go crazy and whatnot. But since they're equivalent, I thinking that this would turn into a way that you can formulate an argument, or using this proof, you can create an argument without certificates.
Of course.
How
No.
you might do it.
You're absolutely right. They're equivalent. I'm just saying that sort of intuitively to think about a non-deterministic log space machine, it seems like a lot harder. Like, I mean, of course, you can all boil it down to what you effectively say is that every step here, there's a non-deterministic choice, and that non-deterministic choice is the path.
No, I totally get that. that's it's easier to think of it in one way or another. But I'm just kind of reflecting what would that converts to in an argument using a non-deterministic machine.
So
and I'm thinking that argument would be that the machine could non-deterministically prove these facts to itself.
Exactly.
You know?
I mean, it's not. You can think of it as the machine non-deterministically guesses B2, and then non-deterministically guesses all the vertices in B2, and then for each vertex non-deterministically guesses the path. So it just cycles over this in order, and then it non-deterministically convinces itself of B2, from which it convinces itself of the subsequent ones. Absolutely. And that is the non-determinism. So you're right. The non-determinism here is simply guessing the path and guessing the vertices. I mean, because in the end, we have broken down the certificate to a large collection of paths. The non-deterministic machine will simply guess all of these paths one by one. Somewhat more philosophically, this viewpoint of a prover and verifier turns out to appear in complexity theory a lot. But I also think it sort of gives you more appreciation of value of a lot of things, especially if you think of things like cryptography and a lot of things nowadays. We talk about Bitcoin and we talk about all these things where there's something that you need to be proven, some fact needs to be proven. This theory sort of gives the foundations for that. How does one prove a fact, even though the machine is limited? The verifier is very limited. It is not able to. It cannot construct this proof, but it can actually verify the proof. So this is one of the deep observations in complexity theory, is that there are lots of non-trivial things that a verifier can do, even though it cannot actually construct the proof itself, which is sort of the essence of P versus NP. But here we're looking at a different example where indeed one can come up with a fairly long and complicated proof for a fact that seemingly the verifier would not be able to deduce itself. And I think I mentioned this in the last lecture, and I'll mention it again. So think of it as, suppose all the computational power in the world, like the cloud or some huge distributed network, computes something. And you want to be convinced that it's actually done an accurate computation, like through a laptop. Then what it could generate through these mechanisms is a proof. And you can verify the proof using your laptop. And these ideas are actually now appearing in practice. Some of these things from complexity theory are sort of percolating their way up. And I've seen more and more talks and more results about that. And this is another example. This is like one, in some senses, almost the simplest example, even though it's fairly complex. Now, as you go down in complexity theory, there are many more complex examples of what a prover and verifier can do. When the verifier is computationally limited, the prover is almost treated as an adversary. The prover has to convince itself of all of its answers. And so again, this is something that you'll have to go and stew on. Like the NL equal to co-NL is not a trivial theorem. But hopefully you see the ideas. You'll have to go back and think a little bit about why is it that the certificate size doesn't blow up exponentially. It's a very important question. And if you really think about it, it's just a collection of paths. Every time is just a collection of paths. Then you will see why it's not growing exponentially. I will end here, and I will take any questions that you have.